Hello friends, let us discuss about the Paulings valence bond theory. We have already learned about the Werner's and Sidgwick's model, and it is necessary to search for new theory because these theories has certain number of limitations, and new theory was invented by the Paulings called valence bond theory. The application of valence bond theory deals with the electronic structure of the central metal atom or ion in its ground state, and the valence bond theory also gives fairly good explanation about the shape as well as magnetic properties of the number of coordination complexes. And with the help of this theory, Paulings devised a very simple as well as satisfactory means of presenting a picture of bonding in various complexes. Now we have go through the outcomes of this particular theory, valence bond theory. Valence bond theory, it is shortly termed as VBT. It is need to the concept of the hybridization explained by the Paulings, and there are certain aspects of the valence bond theory can be explained, and there are certain assumptions based on the VB representation, that is the tetrahedral square planar, trigonal, bipyramidal, octahedral complexes, and each giving one of the examples. And there are another type of concept, that is inner and outer orbital complexes, electroneutrality principle, that is the certain number of ligands can donate electrons, and there are certain spectra or their neutrality is explained with this particular principle. Multiple bonding, that is more than one bond between the metal and ligands in that complex, can be explained with the dpi, ppi and dpi, dpi type of bonding. And there are certain limitations of this theory also, and we also explain regarding this. Now in this theory of valency or valence bond theory, Werner structure and its existence have been explained, and valence bond theory, crystal field theory and molecular orbital theory, these are the important theories we will discuss. Now there are certain assumptions of the valence bond theory. Linus Pauling explained the assumptions regarding the covalent bonding in the particular metal and ligand bonds. For the formation of coordinate covalent bond, the central metal atom or ion in the complex that provides the number of empty orbitals equal to its coordination number, either 4 or 6 or any other, for the purpose of the ligand orbitals which are required for the bonding, and that bonding is said to be coordinate covalent type of bond. And the set of orbitals are formed, that is hybrid orbitals. The formation of this strong bond between the metal and ligand, the overlap of these should be very effective as possible, and for that purpose original atomic orbitals of the metal undergo the hybridization and new set of equivalent orbitals are formed in that hybridization process. And each ligand at least contains a one electron pair for the purpose of donation to the metal atom, and at that time there is a formation of sigma bond, and a coordinate covalent bond is formed when the vacant orbital of the metal overlaps with the field electron field orbital of the ligand. The coordinate covalent bond is considerable amount of polarity also been there due to the mode of formation, and the metal electrons, they do not take part in the hybridization, and that particular orbital or the electrons are called as non-bonding metal electrons. So we already seen in that previous theories, those electrons do not take part in bonding, that is called as non-bonding electrons. There is also possibility of formation of pi bond. In addition to that, there is a sigma bond, and that changes the distribution of both metal and the ligands also. And from this number of unpaired electrons and paired electrons, we can predict the magnetic properties of the particular complex which are been explained in this theory, as well as the geometries of the complexes are also been explained with the help of Paulings valence bond theory. So metal electrons are present in the particular d orbital or maybe the ion, and actually we represent these are the empty d orbitals of the particular uh, metal, and the ligand, these are the ligands supposed to be the tetrahedral or square planar type of geometry, and these electrons these orbitals of the particular ligands are filled likewise. So in this way we can get the hybridization of the particular bonding between metal and ligand. Now if we see the geometry of the particular metal ligand bond, here the metal at the center and ligands to the same line, or that linear way, that hybridization is sp. Metal atom is present at the center, and in that triangular type of geometry, here are the ligands present in this corner. So that is the trigonal planar type of structure, and hybridization is sp2. Square planar type of structure, metal at the center and there are four corners of the square plane, ligands are arranged and it undergo dsp2 hybridization. In tetrahedral geometry, here sp3 and trigonal bipyramidal type of geometry, metal atom at the center and this is a triangular phase, and here we join these particular bonds with the this particular ligand, that is the uh, pyramidal type of structure is observed. There are two types, pyramid upper and lower side, so that is the bipyramid. Hence the structure is trigonal bipyramid and undergo dsp3 hybridization or sp3t. So such a type of structure is exists. And lastly, octahedral structure, metal atom at the center and six corners are occupied by the ligands, and it undergoes D2sp3 or sp3d2 type of hybridization. Now we will discuss about the particular examples regarding the hybrid orbitals. Here the linear hybrid geometry, here s and pz orbital is used, and this example is Ag NH3 by 2 plus. So trigonal planar structure HgI3 minus tetrahedral structure, hybridization is sp3 NiCl4:2 minus, and dsp2 hybridization square planar geometry NiCN4:2 minus. Here is the central metal atom is nickel and here is also nickel, but there is a actual the nature of the ligand is quite different, chloro ligand and here cyano ligand. Hence this has a strong type of ligand, hence dsp2 hybridization. Then dsp3 hybridization trigonal bipyramidal structure, example is CuCl by 5:3 minus, then square pyramid, here NiCN5:3 minus, octahedral structure CONH3 by 6:3 plus, having the D2sp3 or sp3 D2 type of hybridization. This is explained with the inner shell and outer orbital complexes likewise. And after that we will go through the next, that is the hybridization. As know, the particular s orbital and p orbital are hybridized gives rise to two sp hybrid orbital, that is the s orbital overlaps with the this particular p orbital, and these hybrid orbitals are come together and they can overlap and giving rise to sp hybrid orbitals. And here there is a large lobes we can only shown over here. If the sp2 type of hybridization, there are certain orbitals are used for the hybridization purpose. So s orbital spherical in shape, here is a pz and px orbital is used, they can be overlap with each other and they get the particular overlapping and hybridization is possible. Next is the s orbital, 1s orbital and 3p orbitals, which are used for the bonding purpose and undergo a tetrahedral type of geometry. Here the particular angle between them, that is 109.5 degree is the particular angle. Then next is the s orbital, and here are the 3p orbitals, and d orbitals is also been used for the bonding. So sp3d hybrid orbitals are formed, and such a structure is formed, that is called as bipyramidal type of geometry, trigonal bipyramidal. Thank you. Bye bye. Take care.